Hi everybody. In this video, I'll be teaching you chemical equilibrium. So before you study this chemical equilibrium or equilibria, it's the plural, you should have the knowledge, the required knowledge on reaction rates. So if a reaction is happening, A, we say just one-way reaction is happening, giving B. The rate of this reaction, which means the disappearance of A, let's say concentration, over a given time dt, could be measured either, so the rate is given as the disappearance of dt, because if it is a color, we can say the color changing, that sort of thing. Then if you're going to tell the same thing from the appearance of B, the product, that will be dt. But this rate is dependent on the concentration of A. It may be first order, second or third order, but I'm just giving here the basic so that we can move on to study chemical equilibrium. So that rate increases with the concentration of A. So rate is proportional to the concentration of A. And if I put the rate constant, take this proportionality constant here, and then I can write this equation like that. So by combining the rate here, if you take just the disappearance, it's easy, concentration here, dt, then we get all the information we need to integrate and find the rate. Okay, so I'm not going to talk beyond that because that you should have studied by now about reaction rates. What I want to tell you is, if this A giving B, if I say rate 1, and at the same time the reverse reaction or the backward reaction happen as R2, or we can say forward reaction or backward reaction. And when these rates at a given temperature, they become the same, so there you will see an equilibrium exist. So when we talk about an equilibrium in physics, you can say there's a statistical equilibrium or dynamic equilibrium. Static equilibrium. So that is when you say a static equilibrium, that is if you're sitting on a chair, nothing is happening, nothing is moving, but the weight you put on the chair is balanced by the upward force exerted by the seat of the chair. Okay, so in chemistry, we talk about dynamic equilibrium because the rate, the forward reaction rate, is balanced by the reverse or the backward reaction rate. So then we have an equilibrium. So if I write, if I get an example, let me get an example and explain it to you. So we'll say reaction like O4. Okay, we'll put the state here. This double arrow or half of two arrows indicates that it is in equilibrium. It goes both ways, forward and backward. Okay. Now, in this reaction, Now, at the beginning, I want to, before I move forward, I want to understand at t equals 0, we have more of N2O4. We might not have any NO2. We'll say they are in a closed, it has to be in a closed environment. So then we, as the time passes, if I say this is concentration or the reactant, so let us start reactant. At the beginning, we have high concentration and it slowly goes down. Okay. Now you have seen that in rate of reactions. Then normally what happens, if it is only one way, this reactant disappears and the product appears. So at the beginning, product will say 0 and it slowly goes up. Okay. And at one point, this forward reaction and backward reaction or reverse both becomes equal. So when they become equal, that is the equilibrium achieved. So this area is when those two rates become equal and equilibrium is achieved. So remember that. Okay, so about that. Otherwise, normal times, this N2O will completely disappear and only NO2 would be there at the beginning if it is just one-way reaction, because it's both ways, both are happening. Okay, now if I write the rate, I use the word forward here, so I'll put the subscript F. You get K, the rate constant for N2O4, and then rate, I put R to say reverse, K R NO2. Okay, so you should understand this one. But this equilibrium continues as long as we keep the temperature constant. If you change the temperature, the equilibrium changes, but then it again, after some time, the system attains that equilibrium. Okay, so now, so in this lesson, I'm going to teach you the fundamentals and bit extra so that you have the necessary knowledge to answer the questions that are given at a college level, chemical equilibrium exam. Okay. We are not going to go into detail about if we are doing physical chemistry, but this is just in general chemistry exams. Okay, so we will talk about equilibrium constant. The constant when the system attains okay. So for an example, we take reaction MA, M being the stoichiometric value there, and then NB giving, now it is in equilibrium, XC plus YT. You may remember when you're doing general chemistry, maybe semester 1 or introductory chemistry, you had something called reaction quotient. Okay. So which we call Q. Because we express that in concentration terms, we put it as QC, was given by the ratio between the concentration of the products. When I say the square brackets, that means the concentration to the reactants. Okay, that ratio tells us whether reaction is going to move forward or reverse, or it has attained equilibrium. Because at the beginning we have more reactants, right? So the concentration here, reactants is going to be high. So when you divide from a higher number in the denominator, you get a smaller QC. So if the QC value is small, that means you know that it's moving forward because more reactants there. If you have more products, then maybe it is, if it is a one-way reaction, it's nearing the end, because the product concentration increases with time, and reactants going to be less. So from that ratio, we can tell whether it has attained or not the equilibrium. So we have, similarly, we can write the equilibrium constant when the system attains equilibrium. Okay, at a given temperature. If you change the temperature, then it again changes, and after some time, it again attains equilibrium. So if K is the equilibrium constant at equilibrium, we can write the similar thing for product. So, okay, so K equilibrium. But if the K equilibrium is expressed in concentration terms, we can say Kc. And then another way of expressing that is in partial pressure terms. Okay, then we call it Kp. Let me elaborate more on that in a bit. So if I'm writing this Qc, I should be able to write the concentration of C. You raise it to the power of the stoichiometry here, X. And you multiply concentration of D, because these are products. Remember that you have to have a balanced equation to start with. Then you put Y here. And then you have A, concentration raised to the power M. Then B, raised to the power N. Okay, that is Qc. Why we say Qc? Because we don't know whether it has attained the equilibrium or not. But when it attains, call it, that is Qc becomes Kc. Okay. Now, similar to that, we can also express dissect in partial pressure terms. So it becomes Qp. So instead of just square brackets, I'll just write P as the partial pressure of X. When you did gas laws, you came across partial pressure, and Pd to the I power, and Pa raised to the power, then Pb to the N power. Okay, so it's the same thing except that P is in partial pressures. Now, why it could be the same, you can express if you take Pv equals nRT. It's ideal gas. So P N over V RT, that is N over V means number of moles. Volume. Okay, so that is the concentration, right? So P equals CRT. Now these are constant, so you can see temperature is kept constant, universal gas constant. So these are constant. So you can see P is proportional to C. So you can express either in partial pressure terms or concentration terms. That's why it is like that. Okay. So if you don't understand this, you should check this again and again. So just to show this example, let me take an example, actual chemical example. So we say gas giving equilibrium, giving ozone 6236. So that's right, it's gas ozone. So if you're writing QC, we'll still stick to QC at this stage. It will be O3, the product, to the power 2 divided by O2 concentration to the power 3. Okay, so that's an example. So if you're going to express the same thing in pressure terms, right? So this time P 3 raised to the power 2 divided by P of 2 raised to the power 3. Okay, that's it. So you have to understand it's always the concentration of products or concentration of reactants. We get QC, the reaction quotient. But if it is in equilibrium, then we use the word, use the letter K, and it will be Kc if it is in concentration terms, Kp if it is in partial pressure terms. So now if Q value is less than K value, we say we did an experiment, we attained the equilibrium, we measured K. Then from the values given, you can say whether if, okay, so initially if Q, I'll just leave it C or P, it doesn't matter, is lower than KC or P, what it means is the reaction hasn't attained equilibrium. But if Q is equal to K, then it is in equilibrium. If by any chance Q is more than K, that means it has gone past equilibrium. Maybe you are heating it up and it's just moving up the value until it settles down. Okay, so if Q is equals K, that means it's in equilibrium. In this case, it has not yet attained equilibrium. All right, so let's do a small example. Two NO2 gas N2O4 gas, nitrogen dioxide becoming dinitrogen tetroxide gas. You can see this arrow says that it's in equilibrium, or it is a reversible reaction. It may not have attained equilibrium, but it's a reversible reaction. Suppose we are told that when you put 0.1 moles of NO2 0.1 of it is added to a 1 liter of flask at 25 degrees centigrade, right? Okay, so it's clear to you. Okay. The concentration changes. So at equilibrium, the concentrations are, so the NO2 concentration is 0.016 m. Okay, so it's 1 liter, so it's easy to calculate, and we don't have to divide it. We can just see 1 liter means 1, right? So this value is the concentration for initial NO2. So at equilibrium, NO2 has become 0.16. It has reduced from 0.1. It is 0.016 here, and N2O4 is N2O4 is 0.042 m. So if they ask what is the QC before the reaction starts, it's easy. Before the reaction starts. Okay, so before anything starts, we just had, okay, let me it's a different color. We just had 0.1 more. So what is our formula? QC equals, I'll just put P concentration over reactance concentration. It's easy. So we don't have anything there, right? 0. Then we had 0.1, and then stoichiometry is 2, so you raise to the power 2. But does it matter? Because when you divide 0 by, you get 0. So QC was 0 at the beginning. Then when you say it has attained equilibrium, because we are told, then we know QC. So the question is first, what was QC? I'm just giving the question here. QC before the reaction starts, we get 0. But after the reaction attains equilibrium, QC is now Kc, and it is given same way again, product concentration. Okay, here I should, to make it clear, I should put R2. Okay, and then because stoichiometry, so here be again R2. But these concentrations here are the concentrations at equilibrium, the ones that they have given. So put it up here. So the Kc could be written as the concentration of N2O4 at top, because that's the product. You can see that's the product. N2O4 is 0.042, and there's nothing to raise to the power because it's just the same. And then other one is 0.016, the second power, right? So now we have actual values. So when we divide it, you can use a calculator, you will get 1.6 10 to the power 2. Okay, so then we can say that is the equilibrium constant, which is Kc, but what? At 25 degrees centigrade, 298 Kelvin, because you have to specify it with the temperature. That's how we do it. Okay, so anything below this value, if we were doing a series of tests in this, the first one without it 0, then the second one we'll say we did it at after 2 minutes or something, then we will get QC value less than 1.6 10 to the power 2. We know that it hasn't attained the equilibrium yet if we knew Kc value. Okay, otherwise we wait till it attains equilibrium, then we do Kc value, then we know at what point it, after what, how many minutes or seconds it attained the equilibrium, and at what temperature, because it's 25 now in this case. All right. Okay, so a simple equilibrium, writing an equation and calculation, you should be able to do. Then you also should be able to predict the direction of a reaction by getting the QC values, right? So if you get confused by this 0.04 or something, just remember it with integers, complete integers, because it's simple like that. So we'll say you have A, just to tell you the easy way to remember, B. Okay, if you have 1 here, initially it's 0, right? Then QC is going to be the concentration of B over A. I'm telling 1, take it as the concentration terms. Okay, then that's 0, that's 1, then it's going to be 0. So if we'll say Kc value we were given 5, I'm just giving it not 10 to the power 4 just to tell you. Then we'll say after 5 minutes we are going to do QC. Then this time we say the concentration of B raised to the power everything 10, and then A is 5. Now we get a value of 2, but 2 is less than and Kc. That means it is still moving forward and attempting to attain the equilibrium, because Kc should be 5. That's how we do it. So for the exam, if you get a series like that, say, okay, erasers what I've written. So we'll say for a reaction like this, I'll write it below, carbon monoxide. It's a reversible reaction, CO2 gas, that's hydrogen gas. Okay, so they have given you Kc 0.64. Okay. Sometimes they might make it 6.44 times 10 to the negative 1. Okay, because so just because it's -1 or just 0.64 doesn't matter. You just should be able to look at the figures and compare it. Okay. Now then they tell, okay, reactants or products. Sorry, delays. I'm trying to get this to work again. So reactants or product concentration. Okay, and you have experiment 1, experiment 2. I'm not going to write the values. I'm just going to tell you. So experiment 1. Okay, so what are the reactants or products here? CO, CO2 product, hydrogen product, right? So each experiment you find the concentration. So we say you whatever the method, analytical methods available, you get a value here, value here, value here, value here. Then you put into the equation. We just get the QC values because we don't know Kc, right? So I mean, we know the Kc, but we don't know whether the reaction has attained equilibrium at experiment 1 level, experiment 2 time, or experiment 3rd time, right? So we always write CO2. This is the balanced equation. So all the stoichiometry is 1 to 1, 1 to 1. So you just have the hydrogen concentration here and divide by CO concentration and H2O concentration. So all you do is you just put these values and then calculate QC. If QC is less than 0.64, okay, it's not yet in equilibrium. Then experiment 2, you find that. Experiment 3, you find that. That's how you, if you're given a question, that's how you do that. Okay. That's how you answer a question asking whether the reaction has reached the equilibrium or not. But they have given 0.64 and they have just given the concentrations at different experiments. Then you find QC for experiment 1, experiment 2, and experiment 3 and compare with 0.64. How do you go to the calculations? I showed you already. Okay. So when you get the concentration terms, always remember you don't include the concentrations of liquids or solids. So in a reaction, if you have a liquid or a solid, you just ignore them and do not include them in your calculations. Okay. So let me give an example when you talk about this. So there are 2 types of liquid, right? You can say homogeneous or heterogeneous. So homogeneous means all the reactants and products are in the same phase. The solids, all liquids, all gases, that's what it means. So for an example, if you take 2 aqueous, it's mixed in water. So if I take bromine, so always check the status, not the state. Okay, so all the things are in state, the same state or different state. So it's aqueous. So let us see what the products are. So C2H2 aqueous. So that means all the reactants and the products are in the same state, the phase. Okay. That's the three states are solid, liquid, gas. Okay, solids and liquids, we don't include them in the equilibrium calculations. Okay. So now, so if you have, you include all of them because they are all aqueous. Okay, and if you have everything in gas, we include all of them. So if I write for Kc here, it will be. It's good to continue to practice to write Kc several times when you do study this material. And then here C2H2. What happens normally is you forget this stoichiometric value, then you get everything wrong. This video is just the lesson, right? Then I'll be doing some other videos where there'll be questions and answers. Then you will see some variations. Okay, so like that. Okay, so let us take a different one for homogeneous because I want to show you Kp too. So remember, when you say Kc, all these values are because in concentration terms, that means moles per liter. Okay, M, right? No molarity is given by moles per liter. I think that it's connected moles per liter. Okay, now, so in a case like bromine, because it's to the power, that unit becomes like that. Because remember, so it's just how the units appear. Okay, because it's to the power 2. Okay, so let me take something gaseous completely. Okay, so let's say C2H6 gas. If you don't understand after watching this video, you should watch it again. That's how physical chemistry part. Sometimes it's difficult, so you need to. When you watch it about 2 times, then you will understand, and they will, what you have learned would remain in you for a long time. All right, so here all gases. So let us write for Kp. You can express that in Kc as well as Kp. Okay. So here, if you express this as in Kp, what happens is you can say partial pressure of C2H4. It's balanced, always 1-to-1, all the stoichiometric, so you don't have to do anything, times partial pressure of nitrogen. You can put gas here. You can put gas here. Then partial pressure of C2H6. You can put gas. Okay. That's what is Kp. Now let us try to get a relationship between Kc and Kp. Okay. These are partial pressures. Kc is in moles, so partial pressure. Normally it could be atm. Any other pressure terms could be too, but normally it's atm or torr or millimeter mercury. Remember that. So how do you get a relation between Kc and Kp? We go back to PV equals nRT. So P equals, I bring this volume here, and then I have RT. Now N over V means concentration. Okay, so I can say this is pressure equals concentration as C RT, and some books might say P equals MRT because it's the molarity. So I just use as C concentration. Okay. Now let us take this Kp here, what we wrote here. Let's see whether you can do it. Let me erase some of the things so that we have space here. Look at this Kp. So consider this partial pressure for C2H4. We write it like this. Okay. So if I write partial pressure for C2H4, related to that. Okay, more or less here. And it could be written as C2 RT, right? What does it mean? C2 means we can write it this way too, because we are used to the square brackets. So concentration RT equals the partial pressure of C2H4, correct? Because according to this is correct because we are trying to get a comparison. So now at this top we put here, that is the same as partial pressure here. Therefore, we can replace that partial pressure given there with these concentration terms and R and RT. Similar to that, we can do the same thing for hydrogen. We can do the same for C2H6. Okay. Now, suppose you had this power here. In this case, there isn't. Then all you do is you put a power there, the same power, because all you replace is this middle inside part. Okay. Now, so now I'm going to write this Kp. Let us see. I can write same thing here. Kp equals concentration of C2H4 RT multiplied by, again the same thing. If I write it will be concentration of hydrogen and RT. Okay, and divide by concentration of C2H6 and RT. Now, if so, what you can see that we have just replaced this one. If there was a power, that power goes above here, above there, above there. If it is 2, 2, if it is 3, 3, like that. So remember that. Don't get confused. Just write this and see why you didn't get the correct answer, because you have forgotten if there is a power or not. In this case, there is no power. Just there is power, just power. 1. Okay. Okay. Now, so there are two things. You can derive it. Nobody's going to ask you to derive it, depending on the exam you're sitting. But otherwise, you can rewrite this as Kp equals. You can take all these terms together and leave the other ones. So you can C2H4 C2H6, and then RTs you write separately. This RT, the second one. Right. Come back to this one. Now here, if I group these concentration terms, it is actually Kc, correct? It's Kc. So now we have a relationship between Kp and Kc with R in RT terms. What is happening here? So this RT, the entire RT will have power 1. This is power 1. That's power 1, but it's the denominator. So if I take it, all the top ones, it's RT2 minus RT1. Right? Because the bottom part going up, this becomes minus. So the correct way to write this would be RT2 minus 1. Right? What is 2 minus 1? Actually, it is the number of, depending on the number of moles, right? Here, this number of moles here, the difference 1, 2, and 1 there. So we can write it as Kp Kc times RT, the whole thing, delta N, right? The entire thing, remember this, okay? The entire thing, because it's not R separate, T separate, but together. Delta N. Delta N is what? Delta N means what? It means number of moles, N of products. Let's see, 1 and 1 came from the products, right? Minus N of reactants. Okay, so that's how you get the relationship with Kc and Kp. So if they give you Kp, and if you R, and if you know the temperature, and then you know the balanced formula, you can find Kc. If they give you the Kc, and if you know all this, you can find Kp. Okay. So when I say end product, that's the total number of moles in product, total number of reactants. Okay. So when it takes to heterogeneous form, heterogeneous equilibrium, to solid giving lead okay. So here, if you have to write Kc, you write Kc. Solid or liquids we don't count, so this will be the product. Concentration of this is balanced, so we see the stoichiometry, concentration of chlorine minus, and then we don't put this one, so that's it. This is Kc. Right? Yes. Then if we're writing for this one, CaO solid plus CO2 gas, CaCO3 solid, and if I write Kc, you can see the top part is, we don't take this one, we don't take the solid, so it will be what, 1 over CO2, that's it, 1 over CO2. Okay, now as I said, this is just theory I'm telling. The more questions you do, which will be in another video, you will learn more. Okay, so let us see that how certain things you can combine, and you can understand different ways. Okay, because you need to have that knowledge to be able to solve problems. Now if you have A, B, always recognize this is forward, this is reverse. Okay, and if I write the equilibrium constant for this, I'm writing, assuming it starts from A to B, then it's coming back, right? So I will write B, the product, over A. That would be my equilibrium constant. Right? Then if the same reaction, if I wrote it like this, because I start with B and going A, then I will write, so I will write this one C1, first reaction, this is the second, just to distinguish them. Kc2 would be written as A. Now A become the product, and B become the reactant, because we always go from left to right, right? That's the standard we use here. So then what is the relationship with this? You can see Kc is B over A, Kc2 is A over B. So you can see a direct relationship where Kc1 equals 1 over Kc2, right? So if somebody gives you a equilibrium of AB and asks what would be the equilibrium of B, if you write the equilibrium constant for BA, it will be just 1 over. That's something I want you to do. Okay. So suppose another scenario, we have A, B giving here. Now the same reactants are products there, but we change the stoichiometry. We'll say stoichiometry means we'll say now instead of 1 to 1, we'll say it's 1, ratio is 1 to 1. Okay, but we'll say that XA moles, we'll say 5 moles or 10 moles, giving XB moles. Okay, then they're asking what will be Kc. Okay, how do you get Kc? So for this reaction, if I write Kc, it will be B to the power X, right? They're the same. So then when you compare, what you see a comparison, this, the whole part B over A is one, that, So you can see this portion here is the same as here without x and x, right? So therefore, if I want to compare the two, what I should do is I should say kc2 equals kc1 to the power x, right? So if they give you an equilibrium situation where fixed moles, 2 moles giving another 2 moles, right? Then they ask, okay, at the same temperature and everything, if you're reacting 10 moles and at 10 moles, then you do the comparison this way, okay? And make sure it's 1, and the Kc here in this case only 1 mole. So remember, so we just got the Kc1 power to the x, okay? If it was 2 and then 10, then the ratio is 2 to 10, means 1 to 5, so it will be 5. So that at this level, just consider that it was 1. So you just multiply by the x factor here from the molar ratio. Okay, so I want you to remember that scenario too. Now, third scenario, B, C. Okay. So KC1 would be okay. Then KC2, C means KC, right? So the second experiment would be C concentration over B. Now the net reaction, what would be the net reaction of this would be, if I get all together, I will have one side A and plus B plus C, right? These two will cancel out. So I get net reaction is, see, if this was a two-step reaction, so if you have the reaction rates, you know that some reactions, they have more than one step. Okay, so A over C. So for that, if I say this is the third one, I can write KC3 as C. Now see how you can get combine these two to get KC3. Okay, so you will see that KC3 could be obtained if you multiply KC1 by KC2. Why? When you multiply, okay, I'll show it here, because KC3 is given as like that. Okay. Then KC1 is multiply. Okay, so you can say B cancel, B and B here cancel out. So you get, so KC3, when you have two steps, you get individual equilibrium constants and you multiply them by them each other, then you get the net reaction equilibrium constant. All right, so those are the ones I want you to understand here. And then when you calculate this equilibrium, okay, I will save it to the end, because before that I will talk to you about a principle called the Chatelier principle. What I'm trying to tell is to find the equilibrium constant, we find from the initial concentrations, and then we give, instead of actual value, the reaction. So because once, if I do that, then you will get mixed up, and I don't want you to not understand what I'm telling here, because this is qualitative part I'm doing now. Then I'll do the quantitative part. Okay. So what it says is, Le Chatelier's principle says is, once it attains equilibrium, system, if it is, it has to be a closed system really. We say A plus B giving C plus D, and it's in equilibrium. And fix the temperature. So what it tells is, if you change certain factors that keep this equilibrium going, which means we call it, you stress that equilibrium gets adjusted and regain that equilibrium. It gets adjusted a bit, okay? It moves certain ways, but after some time it attains equilibrium. So example, if we increase, so one of the things is first the concentration. Okay, so concentration. If we increase the concentration of A, what happens? You know, from the knowledge of reaction rates, you can say it moves forward. If you increase the concentration of B, it moves forward. So by increasing the concentration of reactants, you move the reaction to the right. So those are the terms. The reaction moves to the right. But if you increase the concentrations, increasing. Okay. If you increase the concentration of products, intuitively it moves to the left. The reaction shifts to the left. So this one shifting. Okay. Shift. Right. What else? What will happen if you increase the or decrease the volume? We'll take a scenario like this. We say, the reason I'm just putting letters is, first of all, you have to understand what is happening just by letters then, because without getting, without making it complicated by putting actual chemicals. Okay. So when you do the questions, I'll do that. So we say A plus B giving okay. See here, 2 moles are there, or 2 molecules, 2 atoms, whatever you call it, right? It's a stoichiometric 1 mole of A, 1 mole of B there, giving 1 mole of C. So if, imagine if it is in a container, and if I reduce the volume, the space becomes less, right? So the reaction would move forward in a way, it will give you only 1 product. Now here 2 reactants there, they will get together and make form. So if you read, it depends on the situation. So always see how many atoms or molecules there on one side and how many are there on the product side. So if you reduce the volume, in this case, more reactants are there. So the equilibrium shifts to the right. Then if you increase the volume, then the reaction shifts to the left. In this situation, right? So if you have a scenario where A gives out C and D, then you can see that if you reduce the volume, what happens? If you reduce the volume, in this case, the reaction will go to the left, because it is producing CD, but it's preferably it's going to go more A, and then it will attain the equilibrium. Okay. Okay. Now, then if you increase the volume, then because you can produce easily C and D, then if you increase the volume in this case, then what happens is this shift to the right. Okay, so it depends on the scenario. Take the same example. what if you increase the pressure? What do you mean by increasing the pressure? Now you know from gas laws, if you increase the pressure, pressure could be increased by reducing the volume, right? So it is the, so if I increase the pressure, these two get together, I reduce the volume. Can you see? It's like reducing the volume, increase the pressure, it moves to the right. I reduce the pressure, it moves to the left. In this case, because there are two, if you move to the other one, it is the opposite happens. So I don't have to go into detail, but you understand what I mean. Okay. All right. So then, what about the temperature? Now, when it comes to the temperature, you have to know whether reaction is exothermic or endothermic. Exothermic or endothermic. Okay. So if I take a reaction like this, A, assuming that we keep the pressure constant, we keep the concentration constant, and we don't do anything else. But if we increase the temperature, so we'll say if we have to find whether it is exothermic, if it is giving out energy, you know these things now. If it is a negative value, then it is exothermic. Always remember, when it is exothermic, it is giving out heat. So if you increase the temperature, it is not in the system. If you increase the temperature, right, so the system is producing heat. So the temperature, if you maintain the temperatures covering the system, what happens if you reduce the temperature here, the heat could give out more, right? More heat could be given out. So by reducing the temperature in a scenario of exo, reducing, what happens? You shift the reaction to the right. Because imagine if you cool the system down, it can produce more heat, right? If you increase the temperature, it moves to the left. In a scenario when it is negative. Okay, so this is easy to remember. That's right. Exothermic is giving out heat. So more heat is giving out. It can give more heat out if the environment is cool, right? So it can give out more heat. So by reducing the temperature, you move the reaction to the right, because when the reaction moves to the right, more to the right, it becomes exothermic. It's easier to give out heat. But then in an endothermic reaction, which is delta H is positive, the opposite happens. Okay, so in this case, if you reduce the temperature, in the earlier case, if you reduce it, move to the right, then it has to move to the left. Okay, increase the temperature, then you move to the right in an endothermic reaction. You have to, this is qualitative, just tell me what happens, you understand the logic of it, and then you remember it. Then what happens if you use a catalyst? Right? We know from the knowledge we gain from reaction rates, the reaction moves like that, and that is EA, activation energy. Okay, so when you use a catalyst, what happens? It reduces that pathway, so reaction happens quick. So when you use a catalyst, what happens? It shifts the reaction quickly, but it doesn't affect the value of the equilibrium constant. It shifts the reaction, but it happens both ways, right? So catalyst speeds up a reaction. Okay, but it speeds up forward as well as the reverse. So speeds up both paths, therefore it attains the equilibrium quickly. forward and reverse, but it doesn't affect no change to K. Okay, no change to the equilibrium constant because simultaneously increases both parts, because once it is reduced here, if the reaction happens both ways, then what happens? It can go this way and they both ways, right? That's what it means. Okay. All right. Now we'll do some calculations. The basics I'm telling you, because as I said, you have to do several calculations to apply them easily. But if you follow these fundamentals, it's going to be easy. Okay. So for an example, we'll take a case where so there are different things in equilibrium constant calculation. They might ask you to calculate the constant, or they might ask you to calculate the concentration of one of the products or reactants. So there's only one they can ask you to calculate, but they have to give everything else. Okay. So first of all, understand what is happening. We say case where ammonia when you're looking at this, it's a homogeneous system. Those things should directly come to your mind. Simply because you have studied about it, right? Now, you can write the Kc for this one, or Kp, anything, right? So let's say we write Kc. So, but the values are different. The relationship is from Kp equals Kc plus Kc times RT to the delta N power. Okay, so remember that. So Kc here is given by nitrogen concentration. Concentration to the power ammonia squared. Okay. Now, initially, if somebody tells us, let me rewrite this because I can show you that. State of any of those they're all gases, it's homogeneous situation. So initially, if I have one mole, okay, I don't have it, I have 0, 0, okay, but from this equilibrium, if I had two, I would get one of each. No, one and the other one 3, correct? So initially I have only 0, 0. Okay, so now if I have a case here, instead of putting 1, if I say I have at equilibrium, I'm asking, okay, concentration changes. So if I take equilibrium, what happens? If I have X, so consider these two as the X, okay, then what would I have here? Because it's 3 times, so it should be 3X, and this should be 0.5X, right? Because 2 becomes 1, that becomes 3. So if I just take X, a better way of explaining. So here, the ratio, so 2 gives 3, so it should be, it's easier to show it like that. So there's 3 over 2. That's what it's coming. Okay. So because when you did general chemistry, we did stoichiometric calculations and limiting reagents. You go for the ratio 2 to 1 to 3. So if we consider something, if you had 2, it will give half of that. But here, you divide by 2 and multiply by 3. So whatever X you get, these are the values you get. Okay, there's no minus sign here. Okay. All right, we'll do similar one now. If you have a reaction C2H2, similar one before, 2Br2, all in gases. Okay, so I'm not going to write down the state, but we should write it down if you're following. It is just to emphasize on something else. That's why. So if I have X here, what would be there? This should be 2x. For x to react, you need 2x. That's how we did the limiting reagents. Remember. And here, the HBr would be x, right? That's what it's producing. Okay, so it's just an example. That's how we do that. Okay, so now understanding that, we are going to find the calculation of equilibrium constant. Okay, so we have K, or we may have to find the concentrations of something unknown, right? It doesn't have to be that. Question. So okay, let us see. Okay, question here. We have iodine 2. Iodide. Yes. So what is this mixture? It's potassium iodide and iodine mixture. Okay. This is equilibrium constant, so nothing with potassium. I'm just telling a solution like this means it has potassium iodide, iodine. That's why it's like that. So then you get 3. So now for this, first of all, let us write Kc. Kc is going to be 3 concentration divided by I2 concentration and iodine concentration. That's it, right? Okay. So we are given what would be the equilibrium constant for the reaction. That's what we have to find, Kc. Okay. So it's if a solution with the concentration of iodine and iodide both equal. So they say initially they equal to 1. So 1.0 10 to the negative 3. Don't get disturbed or like because they have this 1.00 to the negative 3. Okay. As long as you follow the method. And this also 1.0. Times 10 to the negative 3. So it says that both have equal concentrations. At the beginning. Okay, this is at the beginning, initial. Then, so the question reads, if a solution with the concentration of iodine and iodide both equal 1 times 10 to the power negative 3, before reaction gives an equilibrium concentration of iodine, after it has attained equilibrium, let me get rid of this. After it has attained, I means initial here, not iodine, so initial, the first one. Okay, and then at equilibrium, the concentration was, for the iodine only it has given 6.61 10 to the negative 4. Okay, now remember we talked about this x and 2x and x. Okay, these ones. Okay, we have to have that knowledge here in solving that. Okay, they say after the equilibrium we are left with 6.61, right? So this is, I'll make it in an easy way to understand. If you get it, if you have to solve a question like that, you write the equation and see whether it's balanced. If not, you balance it. If there's a necessity to balance it, you write initial concentration Maybe did I get this table and the pen starts right? I means initial. We were given change, then equilibrium concentration, ICE they call it. Initially this is 0. Okay, now consider the change. It takes away X amount. Look at the ratio, stoichiometric ratio 1 to 1. So it will take away minus X amount. Take that as a concentration. Okay, minus X amount from iodine, because minus is taking away. Okay, and then same thing from iodide, and then it will, because 1 to 1, it will give X amount here. We don't know that's X amount. Okay, then Kc is not given to us either. So then the change equilibrium concentration has to be, they have given us the equilibrium concentration, because so, but has to be this 1.4 10 to the negative 3 minus X, which should be equal to, because they gave equilibrium concentration of iodine, right? Should be equal to 6.61 times 10 to the negative 4. Okay, so just keep it there, but if you just write that one, that's enough. But here, because there's a reason, because they gave it, that's why. Then this one at equilibrium concentration, because to calculate Kc, we need the concentrations at equilibrium. So here it will be 1 10 to the negative 3 minus X, same as here. Okay, but only this amount we have given. Okay, come to that. And then this should be just X. Okay, now let us find what is X first. So we find X by getting this part here, 1.00 minus X equals 6.61 times 10 to the negative 4. Okay, so I'm not going to go into detail of solving, but when you solve it, because X is here, so 6.61, you take minus X. That's right. Okay. Minus 6.61 10 to the negative 4. It's recognized, okay, 6, but negative 4 is smaller than negative 3, equals X. Okay, so that when you do the calculations, again, it's the calculator, I get 3.39 to the negative 4 as X. What are these? These are concentrations, so you can use that MMM all the way, but that's the concentration term, right? Now you know that one, so we can find this now. Okay, what would it be? Minus X, it will be the same, right? So now I can write Kc. Let's go back and see what is Kc. Iodine concentration, which will be X, right? X is found here, so it will be 3.39 to the negative 4. Right? We found X, that's there, right? By, we know just iodine concentration times 10 to the negative 4 and multiply by, here also it is going to be the same value, right? Because initially X is the same amount that was reduced from the early one, so it will be again 6.61 times 10 to the negative 4. Then when you solve it, we get the Kc value. Okay, so in this case, let me see, I get 776. Okay, so whatever the temperature it was conducted this experiment and attained equilibrium, that will, this Kc is valid only to that. So that's one way of finding. So what were we asked to find? We were asked to find Kc, but we could have easily found Kc if they give equilibrium concentration of iodine, iodide, and I3 minus, right? They didn't give that. So we had to just put X as the change, but X was balanced here, looking at the stoichiometric values, 1 to 1 to 1. So it was easy for us. But to make it, because we didn't know X, we didn't know KC, we couldn't have, with one equation of KC, we couldn't have found all. So they gave at equilibrium the concentration of one of the things, reactant. So therefore, one of the reactants. So we were able to calculate that. Okay. Now, let us try to calculate if you are given the concentrations values, it's easy, right? I'm not going to do one of them. So if they give, we'll say they gave you the values of I3, I2, I1, you can calculate KCs, right? So that's not going to be a difficult thing. So let's not do one of them. We will do where we don't know X, but we know KC, then how we're going to do it. Okay, so where we had to use quadratic equations. Now, as I said, I will do the calculations on another video, but I want you to understand these steps. Okay, so for an example, so now here we know KC. Yeah, so if we know KC, and we have to find X, the amount reacted. Okay, so we'll say for a reaction, KC is given for a reaction like this. Let me see the example here: PCl5 gas, PCl3 gas plus Cl. Okay, now KC is given as where is it? I can, okay, 0.0211. Okay, 0.021. KC value is 0.021. So the question is, what are the concentration? What are the equilibrium concentration of all these things? PCl5, PCl3, and Cl2. That's the one they're asking. Okay. Initial concentration of PCl5 is given. Initial concentration. You just write down all the things given, and then we will just look at it. Initial concentration given as 1 m. Okay, the MEDTC. So we write down that formula we did it the way we did the table before. That's what I want you to learn from this, right? So you have the table, write it according to those ones. See what we are looking for. Write it. ICP initial. Given initial, yes, they have given initial for PCl5 as 1. Initially, this is 0, the productive. Change, let us put X. Here it's minus, that's plus, plus. Minus means it disappeared, right? So at equilibrium, the concentration should be 1 minus X, that is X and X. So we have only one unknown, and we know KC, so we should be able to find out. So let us write KC first. So this is where you have to remember, okay, PCl5, PCl3. So when you're writing, you look for the stoichiometry. There's nothing to worry about the stoichiometry here. So you just, because 1 to 1. But let me make a point here, PCl5. Now, when you are putting these values here, that X value changes had this been 2, right? That will be 2X, correct? Not in this case, but I'm telling you. So then 2X is what that comes to PCl3 here. While that power is there, because according to that, the original formula should have the power if there was a 2 there. Then inside it will be 2x. Okay, so when you do questions, you will see such scenarios. Okay, now in this case, it doesn't matter. because there's no, it's all one-to-one. It's easy situation. Now, what is Kc? We have 0.0211. 0.0211. Okay. PCl3 is what? X. Cl3 is Cl2 is X. And PCl1 is 1 minus X. Okay. Now, when you get a situation like this, we have to use quadratic equations. Okay. So try to get all x's one side and things like that, but we are going to come across some difficulties. Okay. X means x squared, right? Now, I try to get a quadratic form. So x squared. I'm bringing these ones to the other side. X squared. So just understand the adjustment I have done it here. Okay. X2 is here. I'm taking this one to that side, the other one to that side, right? So when I take that, I get plus 0.0211x minus minus 0.0211 equals 0, right? Then we use this quadratic equation formula. So please write it down. X equals minus b plus or minus b squared. We get two answers. We'll take the most reasonable one, right? That makes sense. So b is this one, okay, and a is here, and c is this one. Okay, so the a, b, c. That's how we. So when you use the quadratic equation, okay. So then I'm trying to find x now, right? That's what the unknown. Once you find the x, we can find the concentration of here at equilibrium concentrations. That's what they're asking us to do. So I'm using the quadratic equation and using those values to get the answer. Okay. So minus 0.0211 because that's the b, right? 0.211. This was plus minus, so you put it. If it was minus, they become positive. Okay. Then plus minus square root again 0.0211. I'm doing this because in case you have forgotten how to do these things, okay. Then minus 4. Then a is the quadratic equation is given by a squared plus bx c equals 0. Okay, that's the method. So here a is 1, right? So that's 4 times 1 times c is 1, right? And then you divide it by 2a. That means 2 times 1. Right? Then when you solve it all the way, that you will get x has 2 values, 1, 3, 5. Positive and as negative. So one will be 0.9 and one will be 0.156. Okay, because this, if you do one set with positive, the other set with negative. Okay, then you get 2 answers. Okay. So when you look at it, okay, the concentrations can't be a negative value, right? Because x means not anything, x means actual value. So actual value, you can't say there's nothing or negative value. So we take this as the meaningful expression. So you get the answers. Concentration of PCl3, the product, or Cl2, which has XX, would have 0.135 M. And 0.135 M. Okay. Then what is PCl5? It will be, PCl5 would be, we deduct that, right? 1 minus 0.135, get 0.87 M. Okay, why is 1.35? You can go here and see that in our table, 1 minus x, x and x. Okay, so that's how you get that. Now, this is a bit difficult, right? So there are times that you can just say one situation when it comes to here. Okay, when it comes to here, because this is where it started becoming quadratic, right? Some situations you can say this 1 minus x, because x is very, very, very small than the original concentration than 1 here, we can say 1 minus x equal to 1, or 1 minus the amount that gets dissociated is so small, we can just assume it as the original concentration. Okay, so then the situation becomes easy. You can just say the whole thing would be 0.0211 equals x squared, right? Because this side is 1. Then you can just find x by getting the square root of this side. But that scenario, sometimes people use it, but there are conditions when you can use it. When Kc value is less than 10 to the negative 3 or higher than 10 to the power 3, these scenarios we can just say 1 minus x is 1, or whatever that the minus x, you can ignore it and just get the value here, which means the initial concentration is so much than that tiny amount that gets dissociated. We can just ignore it for this part, not these ones, for this part. All right, so when you do more equations, when you do more calculations with more questions, you will be able to use the equation in this manner. But the condition is Kc has to be less than 10 to the negative 3 or more than 10 to the power 3. Now here in this case is, what is the case here? Yeah, 0.021. You can see it is more than 10 to the negative 3, so we cannot use it. Okay. All right, everybody, that ends the equilibrium, and then there'll be another video where we will be doing answering chemical equilibrium questions. Thank you.